In mechanics, we tend to treat objects like blocks, or at best, we treat them like point masses, right? So we say, oh, let's put a block on a plane and give it a shove and see how it accelerates. And then when we draw the free body diagram of that thing, we treat it like a point at the center of this XY axis. Um, but when we stop and think, okay, what is the block made of? Well, what is the block made of? So early theories for the composition of matter posited the idea of the atom. Right? So what is an atom? When I first learned this, someone suggested to me the an effective definition for the base unit of something. And I think they use the example of cheese. So let's say you have a block of cheese. Right? So how do you draw cheese? Oh, I don't know. There's some cheese. And you cut that cheese in half, right? And you cut that one of those pieces of cheese in half as well. And you keep cutting, you keep cutting. The base unit for that cheese is happens when you cut it in half and it's no longer cheese. Right? So you cut a block of cheese in half, you now have two pieces of cheese, and you cut one of those in half, you have two pieces of cheese. So the base unit for any thing that you're talking about is the smallest unit of that thing that is still identifiable as that thing. That's basically what an atom is, right? And we have lots more ideas of what an atom is made of. But for us, for now, we'll just say matter, right? So physical objects are made of atoms, and atoms are the smallest units of anything that is still identifiable as that thing. All right. So atoms are what? They're small. So they have very, very small masses, very, very small volumes. And so now we actually have a way of talking about the temperature of things. But before I get to that, I want to do an example. So if big things are made of lots of little things, it's useful to have a handle on what those little things are. All right, so let's talk about the mole. What is a mole? Well, a mole is a number, right? A mole is specifically Avogadro's number. Avogadro's number, again, it's just a number. Avogadro's number is 6.022 times 10 to the 23. And it actually has a unit. It's 6.022 times 10 to the 23 things per mole. So often we'll just give it a unit of per mole. So the unit mole, we drop the E. All right. But again, a mole is just a number, like a dozen, right? So when we say a dozen, we mean 12 things, right? And when we say a baker's dozen, we mean 13 things, right? So if I have, no, that's good for now. That's good for now. Okay, so Avogadro's number there is the number that defines a mole of something. And you can have a mole of anything. Right? Again, clearly we're going to be talking about moles of atoms, but you could be talking about a mole of molecules, right? Or a mole of rocks, or a mole of cats. It doesn't matter, right? It's just a number. Just like you can have a dozen anythings, right? And a dozen some things is too few, a dozen other things is too many. But an Avogadro's number of atoms is, well, it depends on what the atom is, right? Because some atoms are bigger than others. So let's do an example. Here's an example that says the mass of a carbon-12 atom is defined as 12 atomic mass units. What is the mass per mole of carbon-12 atoms? Okay, so I'm introducing here this atomic mass unit, U, right? So one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. It's pretty close to the mass of a nucleon, like a proton or a neutron. It's not exactly, because those masses are different by just a small amount. So the question here is, what is the mass per mole of carbon-12 atoms? Carbon-12 just means it has 12 nucleons, right? As opposed to carbon-13 or carbon-14, which are different isotopes of carbon. Okay, so we're looking for the mass of 1 mole of carbon-12. We also sometimes call this the molar mass. If you've had a chemistry course before, you're probably familiar with what we're doing right now, and that is totally fine. If you have not, that's okay too. So we're looking for the molar mass of carbon-12. Okay. So the mass of 1 mole. So I start with 1 mole of atoms, right? And I want to know the mass of that. So what do I have? I have that the mass, let's write it up here. I have that the mass of 1 atom is 12 atomic mass units. Okay. So we could do this. We could say, let's multiply by Avogadro's number. That's going to get me number of atoms. And then let's multiply by the mass of 1 atom. And that would give me the total mass of a mole of those atoms. All right. So let's do all of that. Sure. So 1 mole, that's just 1 mole, times Avogadro's number is 6.022 times 10 to the positive 23. Again, has units of per mole. That's good because that makes the mole go away. Times the mass of 1 atom, which is 12 atomic mass units. But I'd like this to be an SI, like a total number, like kilograms. So times 1.66 times 10 to the minus 27 kilograms per atomic mass unit. Okay, so if we do that math, times 12 times 1.66 minus 27, I get 0.011996 kilograms. So that's the mass of a mole of carbon-12 atoms. But look, if you convert this to grams, that's really close to 12 grams, which is fantastic. Look at that. 12 grams, and that's 12 grams, let's say, is 1 mole of carbon-12. So that's 12 grams per mole. And it was also 12 atomic mass units per atom. So the mass per atom, in atomic mass units is pretty close to the mass per mole in grams per mole, or the mass per mole in grams. Okay, so what that means is the periodic table gives us numbers, right? Have you ever seen a periodic table? Let's find a periodic table. There's probably an app for that, but you know what? Google's there. Let's just find an image. Which one of these is your favorite? Just need a little more resolution there. There, perfect. So you see this number right here. So we're zooming into carbon. Right there. What's the number under carbon? 12.011. That number doesn't have units, right? Well, it does, but it actually has two sets of units. That number is the molar mass, right? So grams per mole. It's also the mass in atomic mass units of a single atom. Those numbers are the same, or pretty much the same. Again, why is that not exactly 12? Well, because carbon actually has different isotopes, so it's a little bigger than 12 because some carbon has a couple more neutrons than most carbon. All right, and that's how we carbon date things. Okay, that's great. That also means we could read off the molar mass of anything else we wanted, right? So there's oxygen. The molar mass of oxygen is pretty close to 16, right? Pretty darn close to 16. What's the molar mass of like water? Well, water is H2O, right? So where's hydrogen? Hydrogen is here, 1.008. And we just said oxygen was pretty close to 16. So the molar mass of water, H2O, must be 2 hydrogen, so that's 2 times 1, plus the 16 for the oxygen, so that's pretty close to 18, a little bigger than 18. Fabulous. Who knew that table would be so useful? Okay, so let's look back at this example. We just said we just found the molar mass of carbon, right? Mass per mole of carbon. It was 12 grams per mole. So the next part of this is what's the molar mass of oxygen? Oxygen gas. And oxygen gas shows up with oxygen bound to itself. Well, that means, again, I can just read this directly off of the periodic table. The mass of an atom of oxygen, we just said, was 15.999 atomic mass units. It's also 15.999 grams per mole. All right, so kilogram is the SI unit for mass, but molar mass turns out to be nice numbers and super useful. So grams per mole is not a crazy thing to think about. Okay, so 2 of those will give me O2, right? So that's really close to 32. Let's just round it to 32 grams per mole. Easy peasy. Okay, great. So what else can we do with this new atomic model? Now that we can talk about lots of atoms, I would like to talk a little more about that. So I told you temperature is related to kinetic energy. Temperature is actually related to average kinetic energy. What do I mean by that? Well, so we've talked about kinetic energy as half mv squared, right? When an object is just moving with some velocity. But what if I zoom in on that object? So let's say I have an object at rest. What's the temperature of that object? Well, it's not related to the net velocity of this thing, but if you zoom in, right? How do you zoom in? I don't know, like... If you zoom in, I can do better. This object is made of atoms that are all connected by some kind of atomic bond. We sometimes model those as like springs. Right? So all of these atoms are connected by a bond that we can model like a spring. And each of these atoms is wiggling a little bit, right? So there's some wiggle this way and that way, or maybe this way and that way, depending on the mode of oscillation or vibration for these things. So that wiggle has associated with it an average kinetic energy, right? In fact, it would also have associated with it an average potential energy associated with whatever force is binding these together. But I'll say each of these has a K average for each atom. And we relate temperature to average kinetic energy. All right, so the statistics of this is beyond the scope of this course. I will just say K average is equal to 3/2 KT. Okay, so this is literally the average kinetic energy of a single molecule in this object. So again, I told you temperature is a lab scale. It's a large scale property, and K average is also an ensemble property, meaning you can't define an average unless you have lots of things. So I can't define a temperature for a single atom. But if I have a collection of atoms, I can take an average of their kinetic energies, and that I can relate to a temperature of the system, right? So temperature is an ensemble property. Okay, so this is how we relate these. This is the Boltzmann constant. And it is 1.38 times 10 to the minus 23 joules per Kelvin, I think. Yeah, joules per Kelvin. Yeah, that makes sense. It's relating an energy to a temperature. Okay. So that's great. What can we do with that? Surprisingly, we can already do something with this. We can do this sort of thing. We can say, okay, let's just look at an example real quick. So we have example number 4 here. College students working on her physics homework in her dorm. Her room contains a total of 6 times 10 to the 26 gas molecules. As she works, her body is converting chemical energy into thermal energy at a rate of 125 watts. If her dorm room is isolated, meaning there's no temperature in, temperature out, really it's heat. We'll get to that. How much does the room's temperature increase in 10 minutes? Right? Okay, so we have a student in a room. So there's the room. There's the student in the room. Let's let the room be thermally isolated so it's not exchanging temperature with any other system. So she is exhausting heat into the room. And the question is, what is the delta T of the room in 10 minutes? Well, okay. I have this K average equals 3/2 kBT. But what I'm able to get from her is she's releasing energy at a rate delta E over delta T. That's a power, right? That's delta lowercase t. That's temperature of 125 watts. So I could calculate a total energy dump into the room. It's 125 watts times that 10 minutes, which needs to be in seconds, so I'll multiply by 60 seconds per minute. So that gets me the total energy dump. Let's see if I can calculate that. It's 75,000 joules. Okay. So that's going into this room. So that's a change in the total thermal energy of the room, but I don't have an expression for the total thermal energy. But look, K average is the thermal energy of a single molecule in the room, right? Remember, the definition of average is what you get when you take you find the sum and divide by the total, right? So K average is total energy divided by the number of things. So what if I just multiply the n to the other side, right? What if I just do this? Come here, buddy. You come over here. Nope. Yeah. So now I can use my definition of average to figure out the total thermal energy of the system. So let's rewrite that. So the total thermal energy of the system is N times K average. And I have an expression for K average. So it's, sometimes we move the N over. It's 3/2 N K T. So then you can say, okay, I don't know the temperature of the room. I only care about a change. Well, look, the only thing changing on the right-hand side is temperature. The total number of molecules isn't changing, and everything else is a constant. So that means I can put a change on either side. So the change in thermal energy of the room equals 3/2 in KB delta T. That's an expression I can use, because the change in thermal energy is exactly this 75,000 joules, and they told me the number of molecules in the room. So I can calculate this. So 75,000 joules equals 3/2 times 6 times 10 to the 26 times the Boltzmann constant, which is 1.38 times 10 to the... It's a terrible 10 to the minus 23 times delta T. So the only thing I don't know is the temperature change. And what I get for that is 6 degrees. And that's 6 degrees Celsius. It's also 6 Kelvin, right? Because it's a delta T. So we should say 6 Kelvin, but also 6 degrees Celsius. Okay, that's not a small temperature change, but you're not typically in a thermally isolated system. All right, if there's some airflow, you're replacing that air, the warm to air, with room temperature air. So it's not crazy here. So we will see how this average kinetic energy relates to average velocity in the future.